In this section, we're going to gather a bunch of limit laws so that what we can do is avoid those tables that we were making by following these rules and understanding how we can just kind of plug in values to evaluate a limit, but also being aware of when we can't do that. So we'll have to be a little careful as well. What we'll do is also use some algebra tricks to help us out, so we'll get some good algebra review here as well. So where we're going to start is just some basic limits, and that's going to be taking the limit of just our function x and also the limit of a constant. So our first law here says if we take the limit as x approaches a, where our function is x, that's going to be the same thing as the limit as x approaches a from the left, as x approaches a from the right. And at the end of it all, we're just getting a out. So let's go ahead and prove this. What we're going to do is make a graph of our equation y equals x. So that's what we're going to do to the left-hand side here. So if I just graph y equals x, that's our diagonal looking like this. And then what we could do is let's go ahead and plug in some values. Let's say I wanted to look at the limit as x approaches 1 for our function x, and I want to see what that's equal to. Well, x equals 1 is right here, so I'm evaluating this point. And what you can see is as we approach from the left, as we approach from the right, we're approaching this output that is also positive 1. So what x is approaching is also our limit in terms of, one's an x coordinate, one's a y coordinate, but if I was solving this, it ends up just being equal to 1. Let's see what happens if I plug in a -2. So if we're evaluating the limit as x approaches -2 with our function y equals x, then I'm out here where x equals -2, so I'm looking at this point. And as we get closer and closer to that point from the left and the right, we're approaching this output of -2. So what we're doing is our value for a is matching what we're getting for our limit. So we could just make a general rule that for any value of a, because this is our equation y equals x, it's that all of our coordinates would have this relationship. So if we were finding the limit, and the limit exists absolutely everywhere here, we don't have any, I want to use terminology that we're going to see in the next video when we talk about discontinuities. But if you think of those scenarios from last week where the limit did not exist, like where the left and right approach two different values, that's not happening here. No matter where we are on this line, we're getting to the same spot. So when we take the limit for any value as x approaches a, our output, that limit, is going to be a. So whatever value we're plugging in as x approaches a, if we have our equation x there, then that is going to just be equal to whatever x is approaching. So that's one of our basic rules. And what we could start to think of it as is this replacement of, if I have this equation y equals x, it's like I'm plugging in a for x. And in that case, it just leaves me with a. That's kind of something we'll start thinking about with these. Okay, our next one is, what if we have a constant here? What if we just have a number and x isn't even present there? Well, x will be present in the graph because x will be approaching a, but what if we're graphing a constant? Well, the limit, the two-sided limit, is the same as the one-sided limit, and what we're going to be left with is just that constant, because essentially there's nowhere to plug in x equals a. We're just left with this constant. So let's go ahead and see this. If I had my equation y equals 1, that would be graphing the horizontal line like this. And let's say I wanted to evaluate some limits. So let's say I wanted to look as x approaches 2, where y equals 1. So I'm going to where x is equal to 2, and I go to my coordinate, and that y coordinate, so I have 2, 1, so my limit would just be equal to 1. Let's say I did the limit as x approaches -3, where y is equal to 1. So I'm out here at -3, my coordinate, -3, 1. So my limit would just be that y coordinate of 1. So this is true absolutely anywhere. Let's say I just said I have some value a. Every single coordinate is going to be that value of a, and the y coordinate is just going to be that constant, in this case 1. But let's just, for general terms' sake, say we have a graph of a constant. The output is always going to be equal to that constant. So if we're taking the limit as x approaches any value of a constant function, the output for that limit is just going to be that same constant. So it doesn't matter what value of a we're using, it'll just be equal to that constant. And again, like that first scenario, our limit is going to be defined absolutely everywhere here. So what those rules let us do is it lets us get away from the graphs, it lets us get away from those tables we were making, and what we can do is just kind of start plugging in things. So, like this limit as x approaches 0 of e squared. What I want to recognize is e squared, that's just a number, that's a constant there. So if I'm taking the limit as x approaches 0 of e squared, that limit is just equal to e squared. And we're done. So no graphs, no tables, that would just be our final answer because of how the limit of constant functions work. Here we can see we have just our function x, and with that, because we know how y equals x behaves, we can just substitute in. So if x is approaching 2, then what we could do is just plug in 2 for x, and our limit would be equal to 2. Our last one here is more of an obvious constant. So we're looking as x approaches 2, but doesn't really matter with a constant function because absolutely everywhere our limit is going to be equal to 4. Okay, so that's kind of the start to our limit laws. In the next video, we'll get some more to work with.